A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 63. In this podcast we cover topics such as engineering, AI, neuroscience, life and other interesting topics and fascinating ideas to educate, inspire and engineer people's minds all around the world. I'm your host Joseph, and for this episode of the podcast I'm very delighted to welcome Dr. Sara Kaiser to my show. Sara is currently a technical staff member and quantum community lead at Unitary Fund and has spent much of her career developing new quantum hardware in the lab. From building satellites to hacking quantum cryptography hardware, communicating what is so exciting about quantum is her passion. She loves building new demos, tools and partnerships to help enable the quantum open source community to grow. In this very exciting podcast, we covered the beautiful topic of quantum computing, what problems we can solve with this technology, ethics in quantum computing and the term quantum supremacy, Sara's book on quantum computing, including the exercises, resources to delve into the field, and so much more to make you become a quantum researcher. For updates on upcoming podcasts, projects, and videos, make sure to follow me on Twitter as well as on Instagram. To join my weekly newsletter, engineeredmind.sh, where I share exclusive content, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Dr. Sara Kaiser. Hey Sara, welcome to the show.
Hi, thanks so much for having me.
Yeah, it's great to have you on the show. So finally we have someone who is an expert in quantum computing on the show, so that's great. Before we delve into the beautiful topic of quantum computing, can you give us like a 1 or 2 minute bio? Who is Sara and what does she do?
Yeah, so my name is Dr. Sara Kaiser. I've kind of been hanging around the quantum computing field for quite a while now. I did my PhD in kind of quantum crypto stuff. And now I actually work for a nonprofit that helps develop the quantum open source software ecosystem. So it's really fun to kind of be helping to develop open tools for such an early and growing technology. I also write a number of different kinds of books, both for babies all the way up to adults. I really like trying to teach folks about how cool technology is. And I also have a really cute German Shepherd dog named Chewy, who normally is on with me on stream.
Great. This is very exciting. One question before we really jump into quantum computing now. The book that you write for kids or for babies, are you also the author of the neural networks for babies? Really? Yep. Oh, okay. I didn't know that. Because I know these books for babies and I noticed, like I see it in so many places. Okay, that's cool to know.
Yeah, you can see some of them up on my bookshelf, but I have ABCs of Engineering, Neural Networks for Babies, and Robotics for Babies.
Oh, that's cool.
But my co-author on that was actually one of my academic collaborators for a long time.
See, that's cool to know. So everyone listening to the show, if you have babies, so get the books on Neural Networks for Babies from Sara. So as I already mentioned, quantum computing is the topic. It's a very exciting field, a very, very young field, I would say. As a non-expert, maybe you can delve a bit more into that. When we talk about quantum computing, maybe some people don't know at all what quantum computing is. Can you briefly explain what is this thing called quantum computing?
Sure. So the way I like to think about like what a quantum computer would look like or be like in our practical lives is something kind of like a GPU. So it's kind of unfortunate we called them computers because I think that makes us think that, oh, I'm going to replace my computer with a quantum computer. But really, it's going to be more kind of like a specialized hardware accelerator. So just like you have a graphics card that does specific tasks for, games or video editing, you can do probably anything on your GPU, but whether it makes sense to or whether you actually get any speed up out of it, kind of depends on the type of problem. And similarly for quantum computers, there are a number of different kinds of problems that we know we can speed up with that type of hardware. It's not a universal speed up. It's not, not all problems are going to be ones that we actually want to run on quantum hardware. But yeah, then if we look at the actual devices, kind of as the name implies, there's a kind of fundamental physics difference between any classical computer components, which is what physicists very maybe presumptuously call any other types of computers. It means classical physics. governs the behavior of those devices. But quantum computers we often refer to the bits in a quantum computer as qubits. Very creative. But those are basically just systems that behave according to quantum mechanics as opposed to your regular physics. So, there's some interesting things that we can do with that type of kind of fundamental bit or qubit that we can't do with classical ones. So just different resources that will allow us to solve different problems.
Mm-hmm. Can you give us like a few examples on what you could do with quantum computing, which we couldn't solve with classical computers?
So it's not usually that you couldn't solve with classical computers. It just might take like the age of the universe. But this is a very interesting question because we have a couple examples. So like one of the most popular ones that you've probably seen is called Shor's algorithm. So this actually would give us a speed up on factoring large integers. And that is kind of one of the most splashy applications because there are a lot of security applications that really rely on it being a hard problem to factor large numbers. There are other kind of search-based algorithms and stuff like that, like Grover's. But interestingly, this is kind of a very big open question in the field. Like there are kind of like two main questions that, if you look at anyone working in the field, they're probably working on one of these two. One is, as you've probably also seen in the news, building the hardware. So quantum systems are kind of by their very nature really hard to work with because they have to be really isolated from the environment, which makes it hard to do things with them. Mm-hmm. And they usually have to be really cold and they are really small. So that's kind of like one of the challenges. But the other is trying to figure out, to your question, where can we actually use these? So coming back to the GPU analogy, we know pretty well like what we can use a GPU for to speed it up, right? Like basically they're good at multiplying matrices. Mm-hmm. So whether that's machine learning or doing graphics rendering or video editing, whatever, if we know we can reduce it to that sort of problem, that's good. Let's run it on a GPU. We don't exactly have those same boundaries of like what is a good problem to run on a quantum computer. We kind of have like examples in this space, but we don't know we don't know the full definition yet. And so that's something that a lot of folks from mathematicians and, theoretical computer scientists to practical people, kind of like myself, that are kind of exploring, software devs are kind of exploring this from the other side. So, there's interesting, like there's a website called Quantum Algorithm Zoo. Mm-hmm. And that's basically a listing of all the algorithms that we know have any speed up on quantum computers. So they're kind of mathy in description, but that's kind of what me as a quantum software developer works from. I look at kind of what the mathematicians have come up with and try to see if that looks like any type of problem that, I've run into in different software contexts.
Yeah, but when we talk about quantum computing now specifically, do you think there's this kind of a hype trend that a lot of people jump on at the moment, like a bit of like artificial intelligence, data science and so on? And do you think there will be a quantum winter, same as in the AI field? Or what's your personal opinion on that topic?
I mean, in self-interest, I hope there's not. But I think in a very pragmatic sense, there probably will be. As you mentioned, there is a ton of hype about this. And, it's kind of been interesting to see over the course of my career because when I started in 2012, it was still a very academic field. Like maybe one or two companies had internal research departments working on it. But it was kind of the standard, here's the really exploratory stuff. And it was really just an academic sort of topic. We've seen over basically the last 10 years, companies either realizing or thinking that they want to get into it and pouring tons of money into it. Mm. And, hiring folks out of academia, building labs and stuff like that, which is great. Obviously, there's a lot more career options available. You don't have to stay in academia. But kind of the tension that brings is, well, now there's a lot of money, VC pressure, just kind of like pressure to actually make this work. And at least in kind of my opinion, it was maybe a little bit premature. And so, yeah, that's kind of, to continue getting the funding, the hype has to keep going up. You can't, it's hard to make realistic statements that don't like get you fired or don't lose you funding. So, you know, I think most people are trying their best to be, you know, especially those working on those kind of two problem areas that I mentioned before. You know, everybody's trying to do their best, but yeah, I think it can be kind of detrimental sometimes because you know, different news feeds that suggest articles to me that are interesting to read. Whenever I see those, I just kind of like facepalm a little bit. There's always like some real science to it, but just like in the translation from the grad student or whoever's working on it through the journalists, through the editors and stuff, it kind of usually gets a little overblown. But yeah.
That's very interesting, Sarah. So also when it comes to now talking about academia and research, there's this term called quantum supremacy, focusing on the term supremacy here. First of all, what is quantum supremacy? Could you give us like a brief definition of what it is? Is it actually achieved? Because, well, a few people say they achieved it. And why supremacy? I think that also implies kind of a racial discussion when we talk about supremacy, which is kind of a critical topic, but maybe you could start with giving us a definition of quantum supremacy.
Yeah. I think the basic idea that kind of term tries to encapsulate is a concrete proof of a problem or in particular, a demonstration of solving a problem that we faster than we know we can do classically. So it's kind of like because that's kind of the other thing is like we have these theoretical proofs that, you know, if we had a device that had this many qubits and this type of gate fidelity, we know it would work. But the problem is we don't have necessarily the hardware to make those demonstrations is kind of like really far behind. So especially when it comes to justifying your program's existence, you really want to be able to show, yes, this is a real device. This does what we expect it to. And, you know, here's demonstrable proof that, you know, this device is worth it, if that makes sense.
Yeah.
You know, you call it a proof of concept, but where no one's actually proved the concept yet, other than we can describe it theoretically. And yeah, to your other question or comment about the term supremacy, I usually try to use the term quantum advantage. That's especially here in the US and some of the kind of questionable ties in the history of this field to fascism and stuff like that. It feels, at least in my mind, and actually a large sector of the quantum community, that we're not really comfortable calling it that. But because I guess it evokes kind of the feeling of like white supremacy and things like that. So we want to avoid that. And, you know, just like in other fields, you can change a term. Like the term itself is very new, I want to say, like in the last 5-ish years, like it was coined. So, you know, it's not like one of those super entrenched words that you like, I don't know, Bourne's rule or something. You know, it's not something that's like been used for 100 years. It's a relatively new term. And that's why, like myself, as well as many others in the field, there was an open letter published in Nature, actually, of a bunch of people signing this letter saying, please, can we not use this term? But yeah, we can change it. And so I hope that, you know, as we go forward in the field, that we can do that.
Yeah. I very much appreciate your work and also from the community that you take the step actually and are very proactive when it comes to these political discussions and like naming of things and so on. And you also mentioned, I quote you here, that we can do better than people in ML, whoever these people in ML are. And this is closely related to the topic when we have political discussions, so talking about supremacy, that ethics plays a big role. And how can the quantum computing community like talk about ethics or involve ethics more into their research? How can we do better than ML people?
To be clear, I don't think it's ML people's fault. You know, what we've seen in, you know, even just say neural network training, you always the person who collects the data or the folks who feed the data to the model, there are inherent biases in the selection of the data in the first place. And when we see biases in the results of these devices, I don't think it's the result of the neural network. It's the result of the data that we're putting in. So it's just maybe a little bit more clear in showing us those biases. And so, there's been a lot of really interesting discussion and efforts in ML and AI stuff to kind of push back against that. At least, I mean, we're all human beings. We're all going to be biased in some sense. No one is perfectly unbiased. So the best thing we can do is at least, kind of acknowledge and try to note or be aware of those kind of influences on our work. And I think in the same way, what I really hope the quantum computing community the lesson that we can take from that is to be really intentional and thoughtful about what applications we're actually using these devices for. Some of the most prominent funding, especially at the beginning for this field, has been military. And so, because we can build a thing doesn't mean we should. I went to a museum about the atomic bomb in the Southwest at one point, kind of near the test sites. And it was just it was very impactful to me to kind of see all the physicists involved with this who, I'm sure they all had their reasons, but, quite a few of them was just like, let's do it because we can. And, obviously that had huge implications. And I'm not necessarily trying to say that quantum computing will have those level of implications, but, especially as it allows us to, even consider the security application. Like if we manage to get a device that could run Shor's algorithm, spoiler alert, I don't think it'll happen anytime soon because you need millions and well, depending on your assumption, many more orders of magnitude of qubits than we currently have. But that could have serious implications for our entire security infrastructure because, public key encryption systems like RSA are based on factoring large numbers. So that's, how a lot of your browser security works and stuff like that. So, independent of whether I think it's likely those will happen, those are the sorts of questions that we want to consider and especially who we take funding from, how we make our work public making our work public as opposed to secret can also help with that. Those are the kind of thing, just basically thinking about who might use the thing after we make it, as opposed to thinking about that only after we've made it and then trying to mitigate it.
Yeah.
So, yeah.
Is there also an initiative or kind of a group of people that decide where the boundaries should be for researchers? Is there something like that?
In terms of ethical use of results and stuff like that, usually that's at a university or individual company basis. We don't have some sort of I really like the model that actually doctors and healthcare professionals have. They all agree to this Hippocratic oath that do no harm. And then, and actually a lot of engineering, especially civil engineers, have similar sorts of code of ethics and actually ethics exams as a part of their engineering degree. I don't know how practical that would be here, but it would be really interesting to kind of see what that might look like. Just because, as mentioned, each university, company, whatever, does it differently. And, setting some sort of baseline understanding of this could impact people's lives. Think about things, that doesn't even mean don't do it, but just think about the implications before, actually committing or taking the money or whatnot.
Mm-hmm. But we talked about a lot of critical topics now, Sara, and I really appreciate that you really talked about that and made people aware of this. So talking more about the practical aspects now, let's say someone is interested in quantum computing and is kind of a bit afraid of all these big formulas and whatnot, and this term quantum, you really think about big formulas and physicists only are able to do this. What we have are frameworks to delve into quantum computing, like programming, and your beautiful earrings already give it away, like Q Sharp. It's one of the frameworks that you can use for quantum computing programming, but there are also things like Qiskit and so on. How accessible is quantum computing today?
Yeah. So I get questioned. I mean, obviously, I am a physicist coming at this, but I do. It is my personal belief that pretty much anyone, who does any sort of programming or, even like down to high school students, can do quantum computing stuff. Right. I mean, and for the most part, at this point, it means like writing quantum programs. Working on hardware is a little bit harder just because that's where a little bit more of those formulas and like you have to kind of understand the dynamics of those quantum systems. Mm-hmm. But in terms of like being an end user of the technology, or even helping build the stack that goes from the electrical signals that control the device, up to a cloud based platform host, I really think and do a lot of work to kind of make that path a lot easier. So that was kind of the focus of the latest book that I've written called Learn Quantum Computing with Python and Q#. It has a cool lady on the cover who I named Alice. Yes. But yeah, I try to liken learning quantum computing and particularly, as you mentioned, software tools like the language Q# and the Quantum Development Kit from Microsoft, or Qiskit from IBM, or PyQuil from Rigetti. Like, there's all of these cool different platforms, languages, packages for doing this. And, I don't have as much kind of hesitancy of like, oh, I want to do geospatial data manipulation in Python. Like, I need to do some map stuff. There are tons of packages for that. And, to do that, I just kind of like Google which one, Google exactly the thing I want to do. And then, find the package, maybe like try an example, look at the docs, and just kind of iterate there to get the code or the program that I need. And I think that whole experience of kind of like learning a task or solving a problem by learning the packaging or learning the language that makes the most sense for it. I feel like that's a little bit more common and people are a little less kind of intimidated by that. And I really think quantum computing is similar. Like, you have these other packages, you can see the examples, you can read the docs. You really don't have to, like, if you want to learn about the math behind it, which one of the reasons I got into quantum in the first place was it's basically all linear algebra. Like, almost the entirety of anything you can describe about qubits, you represent with matrices and matrix operations. So to me, that was a lot easier than triple integrals and all kinds of like actually kind of intimidating math. So I was like, at the time I was like writing programs actually in Mathematica and stuff like that. And I was like, hey, multiplying matrices, I don't have to do that by hand. I can make a computer do that. And I think that's kind of, why a lot of these software packages can be really helpful is, well, computers are already pretty good at multiplying matrices. So you just leverage, some of the lower level tools to do that and build up kind of an interface for the user that kind of more closely represents the description of qubits more generally.
Yeah. When it comes to the book, now that you've mentioned your great book, where do you start in the book? Like from the first principles, and then what projects are involved in the book, and where do you end the book, or with what project do you end?
Yeah, so kind of as the title alludes to, we use two main kind of software tools to help people learn this. We start with Python, mm-hmm. which is usually kind of a language that at least most people have had some experience with. And that's kind of like the first third of the book. And in that part, you actually work on building your own quantum simulator. So most of my day-to-day work is actually not against hardware. It's against simulators on my machine, which actually are way better than any hardware that we have at the moment. So in that kind of first step, you actually build up your own simulator in Python that kind of shows you like kind of what's happening inside the box. And then the kind of latter 2/3 of the book, we kind of shift to using Q# because so Q#, let me just give the brief description of what that is. Mm-hmm. It's not C#, it's not F#. It is also made by Microsoft, but that's the only utility, like that's the only thing that sharp means. It is an entirely new programming language that is really designed around writing programs for quantum computers. and it's kind of much higher level than a lot of the other tools, like that you mentioned, like the Python tools like Qiskit and stuff. Those kind of focus at the like logical gate level. So, you know, like if you remember from digital logic classes or whatever in school, like ands and or gates, you're writing out how to make an adder at the gate level. So that's, you know, similarly, we have a concept in quantum computing where we have gates and operations on the qubits. So a lot of those tools and packages right now kind of describe that level, which is important because we can't get to, you know, an operating system without describing the digital logic at the lowest level. On a classical computer, kind of makes sense. We need to do the same on a quantum computer. But Q# is kind of like the next level of abstraction where I can just say, like, I want to do phase estimation or something like that, which is, you know, kind of a mid-level algorithm, kind of like bubble sort. It doesn't do sorting, but it's like that kind of level. And that's just built into the language. And so with the libraries and stuff like that. So I really like working in Q#, and I thought this was a good choice for the book because I think it will really kind of give people a flavor of what it looks like to actually write scalable quantum algorithms. Like Shor's algorithm and things like this, yes, you can write out at the gate level, but it gets huge. And just like, you know, we invented high-level languages like Python or whatever because we did not want to write assembly. Similarly, you know, that's kind of the direction Q# is going, is kind of giving us a higher level tool to kind of help us build bigger programs. And so that's kind of like why we use that language for the rest of the book. And each chapter, one of the things I really like about this is each chapter has a game that you're playing. So, you know, you learn a lot of these quantum algorithms or kind of building blocks of quantum algorithms like phase estimation by playing games. Just because sometimes it's hard to come up with a specific application at a building block level, right? So yeah, and at the end of the book, the last couple chapters are quantum applications, and you learn and write out like Shor's algorithm, Grover's search, and also quantum arithmetic. So, which sounds kind of like going backwards because adding numbers on a quantum computer sounds not useful. Should probably, if that's all you want to do, you really should probably do that on a classical computer. But as a part of other algorithms you might want to build, you may need to add or multiply different values and stuff like that. So, yeah, that's. I'm really excited with kind of how it turned out. It took 3 years to write.
Wow, that's a long time.
But yeah, I think it's a little longer than, you know, kind of your normal technical sort of book. But, you know, my co-author and I, Dr. Chris Grenade, who actually works on the Q# team at Microsoft, really tried to put a lot of thought and care into making sure the book is accessible, making sure, you know, the descriptions and code, you know, kind of were the best we could do. And I think it turned out really good.
Yeah, awesome. And for anyone listening and really wants to get the book, I'll put a link to the book down in the description. And with a special code that I provide you with, you can save 40% on the book. So make sure to get the book from Sara if you want to delve into quantum computing. Maybe a dilettantic question, I'm not sure. Because when we talk about like the classical arithmetic on computers, we usually run into things like precision, like floating point precision. Is there like a similar concept in quantum computing? I'm not sure if that's a dumb question or not.
Oh no, I don't think it's exactly a tough question, but it's a fair question. You know, so there are ways we can represent floating points and stuff like that. It's basically by binary encoding. So if you remember doing like, I think it's like okay, now I don't remember there's like a mantissa and you like put the exponent and stuff. So basically how you do it on a quantum computer is you would represent it like that, just like you would at low level on a classical computer. We don't necessarily have a different concept for that. There are other interesting ways of encoding that potentially. So to give you a little bit more details about like how does a qubit differ from a regular bit? A regular bit in our computer can be 1 or 0. And a quantum bit basically has at least one, if not more, degrees of freedom. So that usually what we call, if you're thinking about a single qubit, you can think of it as basically a point on a sphere. Mm-hmm. So you can describe that with two angles, or you can describe it, and those are continuous values. So not just 1 or 0, any angle you want to describe a point on the surface of a sphere. Now that, unfortunately, that kind of perspective, it's called a block sphere. So you can look that up on Wikipedia or whatnot, but or in our book. But that picture doesn't really scale, because some of the other interesting behaviors or properties we have with quantum systems that we don't with classical are things like superposition and entanglement. So those are kind of like part of our operation toolboxes. On classical computers, we have like and, or, not. We have a lot of those as well, but we also have operations that can generate entanglement and superposition. And in those cases, you can't really break that down into like, here's a bunch of spheres that have some sort of relationship. It's an entirely new system you can't break down and describe individually. So, this is another theme we kind of talk about in the book a lot, is like sometimes mental models like that are good, and they can kind of help people get on board. But the challenge with a lot of stuff in quantum is they don't hold up very long. Like there's usually some pretty fundamental things that are wrong about them. And so I know for me, like when I was learning quantum computing, I really liked that block sphere description. Like I'm a very visual person. I was like, great, I can do points on spheres. And most quantum operations are basically rotations then of your point on that sphere. But yeah, when I was trying to understand things like 2-qubit gates or entanglement, it was really hard actually, because I had to like remove that description and come up with a better, more general one.
Yeah. So. That's very interesting, Sarah. Thank you so much for explaining that. Also, when it comes to, I know I have the term flops in mind, like floating point operations per second. Is there like a similar concept in quantum computing, like quantum operations per second, like COPS or something like that? and where's the limit? Where's the limit now? And where do you see it going? Like how is the growth of that COPS, if that even exists?
I don't know if there's something that is as directly equivalent to that. There's kind of two things I could mention that are related to that. Mm-hmm. One of the challenges with working with quantum systems, just more generally, is you kind of have a hardware-based limit for how long your device lasts. Every device basically has a fairly quick expiration date. The reason being is that to see those quantum effects, you do have to keep it pretty isolated, like whether that's by temperature or whatever. You can't, like just via entropy and stuff like that, you can't do that forever. Yeah. And so we call this kind of time that you can work with qubits coherence time. And different systems have different coherence times. Most of them are like sub millisecond. Mm-hmm. So you maybe have anywhere from a couple nanoseconds to work with it to a couple microseconds. So whatever operations you do have to fit in that time. Some systems have times up to like seconds, or I think I even saw a paper that was up to minutes for different trapped ions. But like there are trade-offs to get that sort of lifetime, right? So a lot of the best devices that we have are on the extremely short side.
So is this
which is okay?
Is it comparable to the RAM in the classical computer, this coherence time?
I mean, it would be like if your entire computer stopped existing.
Oh, okay.
So like when you hit that time limit, basically it's like scrambling your data. You have no coherent control of the system anymore. And so it will just kind of like start random things will start happening and you'll have no idea. Like it will be really hard to get your data to read it out or whatever. So it is really like, in the spy movies, like this message will self-combust in 3, 2, 1 or whatever. That's kind of what we're talking about. So that's kind of one thing that is related. So whatever operations you want to get in, it's going to be governed by that coherence time. The other thing is so thinking about kind of benchmarking and like how do we compare different devices. As I mentioned, there's tons of different physical systems that exhibit quantum properties that we are actually, different groups are trying to build qubits out of. So everything from superconducting devices, which are kind of the ones that look closest to most of our classical technology. They fab them actually in the same factories that make computer chips. There are other qubits, though, that are made out of photons or single particles of light. Those are my favorite because I like lasers. There are other ones we make with trapping different atoms and ions in magnetic and laser-based traps. And then we treat the energy levels of the electron in that atom as a qubit. Most of these systems, we kind of like restrict it to two specific levels because those are like the top and bottom pole of the qubit. And so there's, there are lots of different ways you can kind of create these artificial two levels in a quantum system sort of thing. The challenge is each one of these different systems kind of usually have different figures of merit or different benchmarks for describing how good it is. And this is one of the interesting challenges in the field, especially for someone, who wants to invest or someone who's even just trying to understand what the space of different academic groups and companies are doing, is that nobody uses the same benchmarks. Most people select a benchmark that makes their devices look best.
Yeah.
So, there are a lot of academic papers and stuff describing different potential benchmarks, and there are some that most people can kind of agree on, but in reality, it is hard to find one that is like, in some sense, fair to all the different devices because the devices are so very different. So, it's not quite as easy. Like when I was building my PC, you can go to those websites, so you can just compare all the different RAM sticks or compare all the different CPUs, and it gives you all these parameters and benchmarks, so you can just directly compare the two devices. That's a little bit hard to do with quantum systems. So, but there are a lot of community efforts trying to sort out what those benchmarks should be and how we should collect and use those.
Yeah. So you as a quantum influencer and making quantum computing more accessible, what advice would you give people who want to delve into the field? And apart from your book, what resources should they maybe consider? And you also have a Discord channel, which I also entered a while ago. What do you actually do, and how can people get in touch with you and learn more about quantum computing?
Yeah. I think, some of the biggest pieces of advice I can give are, one, don't be intimidated. Like, I know, even when people come up to me, they're like, wow, you must be so smart to do quantum computing. Like, there are so many, like, I'm just a person. Everyone else is just a person. Like, I can look at what other people do, like working on Kubernetes or some machine learning stuff, and I can be like, that seems really hard. I can't do that. So I really think it's just something that you specialize in. And so, kind of approaching it like that, it's a thing that you can specialize into and learn, kind of in, as we discussed before, and pick up a software package or language and give it a try. I'm an experimentalist by nature. Mm-hmm. So sometimes like reading textbooks and stuff, like actually I struggled reading a lot of the textbooks for my coursework. I would much rather be in the lab. And honestly, I learned a lot more getting hands-on and actually trying things. And so one of the things that I find really, really exciting about the field now is we have these software tools to get hands-on. Yes, sometimes you're not actually using hardware in the back end, but you would still be writing the same programs. And so it's really exciting to me. And one of the things that I work on a lot at the Unitary Fund, the nonprofit that I work at, is trying to help people kind of do that hands-on thing and kind of get hooked on like seeing how they can actually have an impact on this field. And that's kind of the other thing that I would point out that can be really fun or encouraging about the field is it's really new. We're really kind of at the point we're still trying to figure out what's the best way to connect these devices. We certainly have a lot of progress, but I think there's a lot of opportunities for folks that have non-quantum skills like DevOps or, people, electrical engineers, mechanical engineers, web developers. I think there are lots of things actually that you bringing those skills to the field can demonstrably make a difference. And like, I don't know, I think it's really fun to kind of be on that bleeding edge and get to influence where the field actually goes.
Yeah.
So other resources I could probably point out. So there's a group called the Quantum QOSF, Quantum Open Source Foundation. They have, it's kind of like my go-to list of resources. So that's QOSF.org. We can put the link below, but yeah, so they're another nonprofit that kind of maintains really good lists of resources, whether it's books, videos, you know, kind of whatever format you learn best with, as well as like a listing of almost all known software tools and stuff like that. So whether you're a Julia programmer or a JavaScript developer, like you can find examples of folks kind of trying to write quantum stuff in those languages, or you can learn a new language like Q#.
This is great. Also, now that you mentioned that it's very, very accessible, actually, quantum computing nowadays with all these frameworks. So kind of a redundant question is then, do you need a PhD for quantum computing? Most likely not, right?
No, I really maintain, and I actually work with a lot of like high schoolers, undergrads, professional developers, like who are bringing these different skills and different perspectives to the field. Because as I mentioned, one of our biggest problems right now is how can we actually, you know, what are the algorithms that will really be kind of the killer applications, if you will? We know a couple, but we need more. And I really feel like getting more people in the field, getting more people interested in this is our best shot. Physicists can only think of so many things. As a physicist, I know this. We're also not very good coders generally. So folks with good coding skills can really help build these tools and infrastructure that will make the field work. So yeah, no PhD necessary. I actually know people who have basically just professional degrees and have been coding for 20, 30 years that are some of the most prolific contributors to the open source space, which is actually another thing I can just briefly highlight. Almost all the tools for these different frameworks, different languages are open source. This is one thing that I find really, really exciting about quantum is like, you can actually contribute. Most of them are on GitHub or GitLab, and you can see the code, you can see, and you can make contributions. So that's something that I, at my job, spend a lot of time working with folks, whether it's trying to help them learn how to do open source contributions in the first place, or trying to find a project that kind of like best matches their interests. And we actually, one of the main things we do is we give out microgrants. So you submit an application and, kind of iterate on the project that you want to do, and we give you $4,000, no strings attached. Yeah. So I think that's been a really, really good thing for the community to kind of inspire some of these tools that we need kind of to plug the gaps, if you will, between, other major frameworks and stuff like that. So you could build those tools. Yeah,
this is great advice. I love it, Sarah. When it comes to the academic side of things, and also, as you mentioned, male or female or whoever you are, you can easily delve into the field of quantum computing. But especially we want to encourage like women in the field who want to delve into quantum computing. And you also experienced some backlash in the academic field. Maybe you can talk a little bit about that, because I think this is something we have to talk about, which is not unnecessary, I would say. So maybe you can give us your 2 cents on how academic people treat women, especially maybe in the field of quantum computing.
Yeah. There's a lot of history and stuff like this. You can see on the news, on hashtags like Me Too, STEM Me Too, and stuff like that. But the culture in academia can be really toxic. Basically, for me, I experienced so much harassment and discrimination and IP theft that I really, for my own mental health, could not continue contributing in that space, which is really devastating, because like I had my whole, like what I imagined I would do with my life was, study a really cool topic, get a PhD, and be a professor somewhere. Like that was the dream. But, kind of as I became less naive, I realized that, there are kind of systems of privilege and stuff that people who look like me, a queer woman, I don't really fit into those correct boxes. And, I know this is the case for a lot of other underrepresented folks in the field. And I think that's, interestingly, one of the benefits of the quantum computing field not being just academia anymore. To be fair, toxic cultures and work environments also exist in tech and in tech companies. But it might be slightly better on average. Slightly. So like I found transitioning to working in industry, I actually worked between finishing my postdoc and working where I do now. I worked in just general engineering consulting, and it was a refreshing change from a lot of the kind of crap that was going on in academia. And that's kind of one of the other things that I really focus on in doing a lot of the community building and stuff that I do, both for Unitary Fund and kind of for my own, the Twitch community and folks that are on my Discord. Things like codes of conduct are really important to me, making sure that spaces are safe for everyone to be there, which unfortunately is not often the case in academic spaces.
No, that's right.
But yeah, just trying to make sure that everyone feels comfortable in these spaces and feels encouraged to contribute. It's not just like, here's the deep end of the pool, good luck. It's not wrong to like need help along that way. Like, we have this ideal of someone who's just really smart and can just sit down and learn the things. I don't know really anyone who's like that, even in quantum computing. We all work together on the coursework and, working in the lab, you're working with other people, you're writing papers with other people. And so it really is a kind of a collaborative experience, which is, why it is really important to me to make sure that, the people you're collaborating with respect you and kind of work with you as opposed to against you.
I think that's beautiful, Sarah, because the thing is also especially when we talk about Twitter, like, which is a very toxic place, can be a very toxic place depending on who you follow. I think especially when we look at the AI community / ML community, it's more like you think about, hey, maybe I should do a video about this backprop algorithm, and you see people bashing each other like on high level stuff, like, well, maybe I'm not going to do a video because the AI community might bash me for that. And I appreciate that you in the quantum computing field take this step forward and say, hey, you could be new, you could be like an experienced program. We are all together in this and we work on something together rather than being a loner.
Yeah, for sure.
Yeah, very interesting. To close this very interesting conversation, are there any last encouraging words from Sara to the quantum computing community, aspiring quantum researchers or whoever is listening to the podcast right now?
I think my favorite option for this is quantum computing isn't magic, but you are.
Oh, this is sweet. Yeah, I like that. Awesome. It was so nice talking to you, Sara. And as we already mentioned, I'll put a link down to all resources in the description. And if you have any questions, you can follow Sara on Twitter. She's quite active there. And you also live stream on Twitch. When exactly?
The schedule is kind of in flux right now, but usually I stream a couple times a week. I do live coding, so you can watch me write code for quantum computers. I also have my dog on stream, so if you need just some cute fluffy dogs, they're also there. And I also do like usually some sort of office hours and stuff, whether it's on Twitch or on my Discord, or on the Unitary Fund Discord. We also have a pretty active, just focused on kind of quantum open source stuff more generally. But yeah, they're all really great places to kind of find other folks that are interested at the same level as you learning, create a study group, whatever, and ask me questions too. So I'm always on Discord.
Beautiful. And if the fluffy dog isn't convincing you guys, then I don't know what will. Thank you so much, Sara, for participating in this podcast. It was a pleasure.
Yeah, thank you so much. I really enjoyed being here and discussing this stuff.
Bye-bye.
Bye.